Hello and welcome. Here we are in lecture 18. Make sure my audio is working. Yes, it is. Great. Um, and here we go. So, as you can see from the title of today's slide, we're talking about power in design space exploration. Let's put that in the context of what we've been talking about the last few weeks. So, if you remember, about almost more than a week ago now, we shifted gears and went from details of the language and kind of zooming out more and kind of appreciating more of the hardware background, what we're doing in the design process. We talked about things like, what does it mean to even do physical design optimization, and how do you optimize for memories? How do you optimize for latency? Today we're talking about a few more things. We're talking about power, which is a really important design constraint in the modern era. And so we're going to kind of talk a little bit about just the background about how power is expended and how can we impact that as a designer. And they're also talking about something called design space exploration, where we've been talking all along about how we want to build these generators and have those parameters and knobs. And the question is, well, how do we tune those knobs appropriately? So let's get to it. So as I said, we're talking about power and design space exploration, or DSE for short. So why is power so important? Well, for many hardware design projects, it often is the biggest constraint, right? That's the most important one, oddly enough. Let's kind of make sure we get our terminology correct here. So maybe people say the terms power and energy. They aren't quite interchangeable, right? So remember, power is a rate. It's, the expenditure of energy per unit time, per second or whatever, versus energy is the, accumulated amount of energy expended, right? So to kind of keep those two things separate. Okay, so when your device is operating, it requires some amount of power while it's running, right? And then, you integrate it over time, and that's how much energy is consumed, right? And so depending on what system you're worrying about, you may worry about more about power or more about energy or both, right? So why is energy a problem? Well, energy is a problem because of a few things, right? For things like mobile devices, of course, energy affects things like battery life, right? The less energy, the more energy your device will use. That's going to change how big or small your battery is or how long or short the battery life is, right? That's the case for mobile. Then, of course, when you're not mobile, there's a question about who's paying the power bill, right? And so we always say the power bill is the one you're paying utility. Really, it's your energy bill, right? You're paying for the aggregate amount of electricity you've consumed. And yeah, in that case, especially for a data center, you're going to care a lot about your energy bill, right? And so so just reducing your overall consumption would be important. Meanwhile, why might power be important? Well, power is kind of important for two reasons. Number one is thermals, or heat, right? Where when your electronic device is consuming power, is they can perform computation, and obviously the computation is kind of the goal, but it's going to produce heat, and actually quite a bit of heat. If you look at the power going in versus how much is actually being used to perform the computation, the majority of it is actually going to be turned into heat, right? And so it's really important to kind of be aware of that. And so even something like a mobile device, like let's say your smartphone or something, which you can't see because of the green screen, peak power is a real problem, right? Because it's quite possible, even with these smartphone chips, or if they really run them, full tilt, full max power, it actually can get too hot to hold, right? And that's not good, right? Nobody wants to, be unpleasant or even burn their hand, right? And so they have to consider that. Okay, well, how hot is this chip getting? How hot this chip could get, and make sure it doesn't get too hot. Doesn't want to burn your hand, right? We've probably all experienced a warm laptop at some point, right? Or laptop's getting too warm, right? And so it's important to make sure it doesn't get too hot. Sometimes if it gets way, way too hot, you run the risk of damaging something or hurting somebody, so you have to make sure it doesn't get too hot. But even below that point, not good things happen, right? Things wear out. It shortens the lifespan of various things. And so you really want to kind of have a good understanding of how much power you're going to be expending, how much heat it's going to be producing, and understanding the constraints the design you're dealing with to know how much heat it could dissipate, right? For example, a smartphone, basically has not a lot of heat dissipated capability, right? There's not a fan in there. There's not a heat sink. It's, a thin, slim device, right? Versus, maybe like a big desktop PC, you can put in, a big fan, a big heat sink, or even a water cooler or something, right? And so you kind of appreciate that. Of course, most modern electronics now have, abilities to measure their own temperature and then throttle and slow themselves down to reduce their power expenditure if they have to. But, it can be a problem. So that's just the heat issue for power. Another issue for power is just actually building the equipment, right? So a lot of the circuitry that goes into your electronic device is there to deliver power to your, your compute, your chip. And all that circuitry for power delivery is sized based on how much power it demands, in particular the peak power, right? And so if your device, normally takes very little power, very low average power, but then, has these periodic points where it, uses up a lot of peak power, you're gonna need to put in a bigger peak power supply to handle that peak, right? And so it's going to be more expense. Sometimes when you have these bigger power supplies, they're less efficient. And so, yeah, as we talked about before, it's kind of this common engineering trade-off where you would like to kind of, reduce the gap between your peak and average whenever you can. This is definitely true for power delivery. Cool. And so it's a lot of details on power and energy. Maybe I'll just pause here and wait for any questions. Cool. Okay. Well, we can keep going. So, given that kind of background about just general motivation for why power and energy are kind of important, let's kind of appreciate where we fit in to this picture, right? So, the high-level equation you see above here, people use to express power, or I should say dynamic power in a circuit, is given as above, right? Basically, the power is proportional to the product of all these terms, right? And so the reason why I brought out the equation is not because we need to solve this equation in this class, is more just that realizing if you can decrease any one of these terms will decrease power. And we as a designer have an ability to impact any one of these terms, right? That's kind of why I'm pulling this out here. So what are these terms? Well, if you think about what's happening when you're spending power in an electronic circuit, what you're really doing is you're kind of charging and discharging things, right? If you were in steady state, you had the same inputs coming in, the same outputs coming out, and nothing changing, you actually won't be burning a lot of dynamic power. You might be burning some static power, but dynamic power is really kind of proportional to you changing things, bits flipping from one way to another. And so really, how much power do you flip from, how much power do you consume when you're flipping bits? Well, going through these terms, right, it's, how much, capacitance or how much energy is going to be kind of contained when you flip a bit. The voltage which you're flipping it, and notice the voltage is this quadratic relation, right? So if you're running a lower voltage, this is a small difference with a huge difference in power. And then the question is, well, how frequently are you switching? Well, there's kind of two things to consider for how frequently you're switching. There is the activity factor and the frequency. So frequency is the clock rate. We're used to that, right? But realize that not every transistor, every logic gate changes every clock cycle. So to account for that, there's this activity factor, which is kind of, on average, how often does it change, right? Realize, for example, in order to reach an activity factor of 1, that would mean that wire is changing every single cycle, which is actually pretty rare, right? The reason why is you think about it, like, let's say, for example, I had a wire that, alternated, right? It could randomly change. Let's say it's 0, and it'll randomly, if the uniform probability goes 0 to 1, 1 to 0, just randomly changing. Well, if it's randomly changing, there's 50% odds it'll have the same value 2 cycles in a row, right? And so as a result, your activity factor would be actually 0.5, right? So that activity factor of 1 is actually pretty hard to do. If you look inside of like a processor, interestingly enough, and you try and track the activities and which things have the highest activity factors, sometimes processors have some sort of registers kind of counting how many cycles they've been operating. And so that counter is being incremented every single cycle. And so you might say, oh, wait, clearly that counter is going to have a high activity factor. And actually, well, the lowest bit that counter does, right? The lowest bit that counter does toggle every cycle, right? Remember how, counting in binary, 0, 1, 0, 1, the lowest bit, but then it's, waits a while before the next bit. So actually, each bit you go up in that number in significance, it's going to flip half as often, right? And so it turns out that, actually many of those bits in that thing, if you look at them individually, actually are also going to have pretty low activity factors. So the reason I'm telling you all this is basically, as a designer, you can impact all of these terms, right? And so reducing any one of these terms, because the product will reduce the power. Cool. So how might we reduce the activity factor, for example, what we're discussing? Well, if I can, make things switch less often. Well, how might I do that? Well, one way to do that is to recognize when things are idle or not being used and put them to sleep and reduce the activity factor. Or maybe you're in a situation where they don't care and you actually don't care to be used in a way to save power, right? So recognize these things are idle and put them to sleep, you can reduce the activity factor, number one. What about capacitance? It's kind of a weird thing to hear from a designer. Really, the way you can think about it from our point of view is actually just area, right? If I have a smaller design, it's going to have less capacitance, right? That's going to save a bit power because, less to charge and discharge. Now, you might ask, what's the relation with capacitance to process technology, for example? If I, go from a 10 nanometer process technology to a 7 nanometer process technology, what happens? Well, each of those resistors does get smaller, so the capacitance actually will be reduced, right? So if you have the exact same design and you use a newer process technology, your capacitance should reduce, right? To some extent, right? And so as a designer, really, the capacitance is mostly kind of set by your process technology and then how small your design is the biggest thing you control. Make your design smaller, less area, you'll have lower capacitance. And then finally, I put frequency and voltage together. And I'm going to kind of mention this over and over again in this course, and I'll kind of remind you right now that the reason why these two are kind of discussed in tandem is that, frequency, of course, is how fast your circuit operates. But if you can, quote unquote, reduce your critical path to run slower, so to speak, you can slow down, lower the voltage, and thus you can save power, right? Because basically, if you lower V, that's great. So even for the same frequency, if you're going to way to shorten the critical path to allow you to lower V, you're going to save a lot of power, right? So you can kind of see these kinds of things. So usually frequency and voltage are kind of set very careful relative to each other. There's a relation there. Cool. Any questions on this so far? Cool. Okay, so let's say your manager's walked into your design office and tells you, hey, your design's burning too much power. We need you guys to get a handle on that. What could you do? Well, the biggest thing is, turn things off, right? If you're in your, apartment or home, hey, I can turn the lights off when I'm not in the room, right? I can turn TV off when I'm not watching. These things are kind of, common sense, and the same is true in a digital circuit, right? So turning things off is a great way to save power. The process of turning this off, terminology-wise, often called as gating, and that is, you're kind of gating the power to that thing. There's actually two types of gating. There's what's called power gating and clock gating. And so what's the difference between these two? It's a little bit of circuit level detail, but they do both are options for us, right? So power gating is we're literally going to say this entire block in a circuit, as the name implies, we're cutting up the power. So supply voltage, gating that, right? There's no supply voltage being applied to this portion of the circuit. Like this thing is basically unplugged, right? It is off. And so this is kind of the most heavyweight thing you can do when you have, some portion of the design, when you say this entire portion we're going to turn off. And so obviously when you turn the entire thing off and you want to turn it back on, there's some latency penalty for doing this. But, this is our heavy hammer, it's a big hitting way to kind of, really save power. And if you aren't using something, this is definitely what you want to do, right? And for example, let's say on your laptop, this has a fancy laptop that has two GPUs, right? It's an embedded GPU and, the fancy discrete GPU, right? If you are using a discrete GPU, kill the power of that thing, right? Turn it off, right? So that way, you aren't burning power on it, right? And so, yeah, power gating, you're just completely cutting off the power. The clock gating is a different one. It's a little bit interesting, right? So the clock gating is recognizing, going back to activity factor, that, if things aren't changing, we can save power. If things aren't changing, we can, reduce our activity factor, and reducing activity factor and save power. And so what clock gating is recognizing is that, this is a portion of the design where it also is, not currently being needed. That's why we're able to kind of, turn it off. But we're going to turn it off in a way that is going to be faster to kind of turn on and off. So rather, power gating, which might take, hundreds or thousands of cycles for something to reactivate, clock gating, like a 1 cycle penalty, right? Maybe 2 cycles or something, right? So it's a very small penalty. Not going to save as much power, but it's much more fine-grained, can be done much more carefully. So what you do is you recognize, for registers, if I prevent them from changing, so we say kind of turning off the clock, but really it's more just preventing the register from changing. If the registers don't change, all the logic gates that follow those registers also don't change, right? So this actually can save quite a bit of power. And part of why you're doing this is you aren't just saving the power from the bits flipping in the registers and the logic that follows them, but also if you think about activity factors for a second, what would be something that would change every cycle? The clock, right? The clock doesn't just change, it goes from 0 to 1 every cycle, right? So that's a really high activity factor. It's actually like an activity factor of 2, arguably, right? And so for these portions of design, what you're going to do is you're going to not only kind of make these registers not change, but also going to prevent the clock itself from changing, right? So that wire is just, changing twice per cycle, you're not going to be disconnecting, right? And so, yeah, in order to have your registers not do something silly when the clock is gated, there's a little bit of extra circuitry put in there, but it's going to save quite a bit of power, right? And what's interesting about clock gating is this was something that was, really, really cool technology, in the late 90s, early 2000s. And, for the last 10, 15 years, it's something that, CAD tools do automatically, right? So, uh, in the spirit of make the tools do the work, this is definitely something tools do well. So really kind of as a conversation about clock gating, the conversation isn't that can the tools do this, the question is, what did I do wrong in my Verilog to prevent the tools from doing this, right? And so sometimes depending on semantics, if you have the way your design written, right, like any situation, would it be hard design tools reading, Verilog, or, even C being read by compiler, the tools normally aren't allowed to change the semantics of your design. So you'd be very kind of conscious of semantics you're requesting. And so sometimes you have a case where you have a register, and even though the value to you as a designer is something you don't care about, if you just have a regular register there, a register is going to change every cycle when this input changes. And so as a result, the design tools don't know that this doesn't matter, right? And so kind of what you're doing is you're going to say instead, you're going to kind of give the change the semantics of your design. So changing the semantics, you're going to let the tools have that freedom to come in and make those changes, right? And in particular, what you want to do is to put a write enable, right? Use one of those reg enable and chisel, of course. And what that does is, of course, when the enable signal is false, the register can't change. And so interestingly, what you're going to do is, even though they're valid registers that don't care, by turning it to disabling in the writes and kind of latching onto the last value you did care about, that's going to let the CAD tools recognize, oh, wait, I can clock gate this. So a lot of times the clock gating optimization passes are going to look for registers that have these write enables on them, and then realize and kind of tie the write enable to the clock, so that way if the register is not going to change, it's not going to have a clock coming into it. And if you're back of your mind, if you're wondering about the circuitry added to do clock gating and to kind of detect the stuff and the write enables, doesn't it have some amount of overhead? It definitely does. But normally in our designs we have not just single bit flip flops, usually registers, 32, 64 bits, whatever. And so we're able to kind of amortize that single bit signal over those many bits. And so usually it's actually not that bad. Okay, more circuit stuff, but we're almost out of circuit stuff. I'm checking in the last questions so far. Cool. So to summarize for turning things off, power gating, that's a big conversation with your physical design team about. I know architecturally this block is not going to be needed at all. We can turn the whole thing off, but this is very much a conscious design. There's a conscious power switch in that portion of the design, and you do it. Clock gating is something the tools are going to do automatically if you let them, right? And the secret is recognizing registers that otherwise would toggle frequently and have long periods where they have situations where you don't care about the value. By simply just making those write enable registers have actually ability to kind of turn on or off writes, that lets the tools go in and do clock gating on them. Cool. Okay. So those are kind of like the design level things. These are kind of more architecture level things we talk about next, about how to kind of save power and energy. So normally for your application, right, you'd love to go as fast as possible, use as least energy as possible, right, and all these various things. But at the end of the day, there's kind of like, some weighing of trade-offs and some kind of choosing of targets and metrics, right? And so when it comes to reducing energy, normally if you're trying to reduce energy consumption, you've kind of in your mind already set there's some performance target, like we meet this performance target, then I want to minimize energy, right? To do performance and energy at the same time is kind of they're tugging each other, they're fighting each other, right? And so you kind of have here's my goal for one, what's the other one, right? Maybe your goal for a smartphone is we know how big the battery can be, we know how long the battery life needs to be, get me the most performance you can under that energy budget, right? Alternatively, you might say, what, I know to play video, we know the video standard format, we know we need to go 60 frames per second for this kind of video, so the performance target's set. And then I want to, minimize energy consumption, maximize that battery life, right? So make it take as little energy as possible to play that video, meet that performance target. So whatever your target is, you kind of got to pick, okay, I have an energy target, maximizing performance, or I have a performance target and then minimizing energy. So right now, let's assume we're, minimizing energy, so we have a performance target. And so what you're going to try and do is you want to set your voltage and frequency to efficiently meet that target. So as we've kind of been talking about, well, if you're able to set your frequency to the right level, so that way your frequency is such that you at that number of cycles per second, you get the result you need. That's going to have a certain clock period, right? And based on that clock period, you're going to figure out how long your critical path is relative to that, right? And if your critical path is a lot shorter than that, you have the option to actually decrease the voltage. And by decreasing the voltage, you can it'll slow your circuit down, but you're gonna save a lot of energy. Remember, as we said in that power equation, right? It was V squared, voltage squared. So you really want to do so. This approach is sometimes called crawl the deadline, where you're like, you know what you need to do. You're gonna use every last nanosecond to get there, and you use a lot less energy doing so, right? And so this is kind of one way of doing it. More generally, you may hear about in processor design, you hear something called DVFS, or dynamic voltage and frequency scaling. This is a standard technology used in many, many application cores. And that is they recognize that, the performance target may change, right? And so when you change performance target, you're going to change your frequency. And based on you changing the frequency, you're also going to change the voltage, right? And so that's just done automatically. Right? There's people who design this in the physical design team. They're going to figure out, okay, for this chip, we characterized that we know that for every one of these voltages, every one of these frequencies we want to run at, what voltage meets timing, right? And they're going to know those voltages. That when you change the frequency, you're also going to change the voltage, right? And so sometimes they pre-characterize the chips. Some very advanced chips actually have what's called a canary circuit, where it's actually a circuit that is representative of the rest of the chip, and they can see if that thing is or is not making timing, and they can change the voltage on the canary circuit to then see how to change the rest of the chip. But however they do it, the result is that you want to increase frequency, you want to go faster, it's going to cost you more juice, right? You got to turn the voltage up, right? If you need to go slower or lower frequency, you can turn down the voltage, right? And so, one approach is kind of just crawl deadline, right? You say, you know what? I know what performance target I have to reach. Turn down the frequency to set the frequency to meet that performance target, and then turn the voltage down to just barely meet that deadline. The alternative is sometimes you, rather than crawling deadline, something called race to halt, right? So it's kind of two different modes here, right? So what's race to halt? So crawl deadline is saying, you know what? If I'm trying to minimize dynamic power, I'm going to reduce that V squared term and really kind of reduce that. Race to halt isn't about dynamic power. Race to halt is about static power. So so far, we're kind of talking mostly about dynamic power. Yes, our power consumption or chip is caused by me switching things, by me doing various things. And this is kind of proportional activity in some sense, right? Turns out a lot of power consumption is also what's called static power consumption. That is stuff that's agnostic to the things you're doing. So at the circuit level, static power happens from things like leakage, where your transistors aren't perfect, and so even if they aren't changing, some amount of power is getting dumped to ground. But even architecturally, there's some amount of power burn, what's called static power. It's just things that are kind of always there, right? So like, just to keep your platform on, there's kind of a certain amount of stuff that's always running, and that's just always burning power. And so with the race to halt methodology, instead you say, you know what, I have a deadline. I'm actually going to sprint as fast as I can, and then I'm going to turn tons of stuff off. I'm going to go to sleep, right? So the halt in this case is going to sleep. And so with race to halt, right, you are going to burn more dynamic energy because you're going faster, right? You're running at a higher frequency, you're using more voltage, you're going to burn more dynamic energy. But the reason why this might pan out in the end is you're going to use less static energy, right? Because hopefully you can turn things off and reduce that static power. And so these are kind of two different philosophies for how to save energy. And if you look at a design, you realize that in common practice to actually do both approaches, depending on what you're dealing with, right? So if you go back to that scenario I gave you a second ago about maybe like a smartphone playing a video, you will see a little bit of both, depending on which portion of the system you're talking about. Where, believe it or not, you think of you're playing a video. Oh yes, I'm watching a video at 60 frames per second. My smartphone's busy and active, right? And not quite, right? So 60 frames per second at the human time scale is an eternity per frame in the compute time scale, right? And so, yeah, there's enough time for your smartphone to, do all the decompression you need to do to render the next frame, load that up, and then actually go to sleep, right? And sleep for milliseconds until the next frame. And so sleeping for milliseconds is actually well worthwhile. And the same thing's true for the radio chatter, right? Where if you're talking about your smartphone sending stuff to the radio, if your phone, when it's talking to the cell tower, has negotiated, okay, my next time to transmit is going to be, this many milliseconds, your cell antenna is actually going to turn off for that time period because, I'm not going to be transmitting. Shouldn't be expecting to receive anything. That's going to turn off, right? So actually, in like a mobile device, in order to battery life be anything useful, it's actually mostly turned off and just kind of turning on for these really small bursts to either render the next frame for a video or to talk to a cell tower, right? And this is pervasive in the design process, right? For example, Let's say you're looking at a website, right? Humans, when reading websites, they'll look at something, they may scroll, they may tap a link, but there's going to be time periods, sometimes even seconds, but at least milliseconds where they aren't really giving it more stimulus. In that time period, the processor can go to sleep. The radio can go to sleep, right? So you can save energy that way. So Racetohalt is definitely commonly used. So is crawl deadline, right? So crawl deadline is like, standard practice basically when you set your voltage for DVFS. How do you know what voltage to set your thing to for frequency? No, given your frequency, you can set the voltage basically as low as you can to meet it, right? So that's crawl deadline. So basically, in a modern design, you're really going to see both at any given time. But I just want you to be aware of these kind of terms and kind of how they matter as a designer, where understand, you may have a target operation, right? Some things like an application core, you may have multiple operating frequencies. For very specialized hardware accelerators, maybe you have a single operating frequency, but either way, both Racetohalt and crawl deadline are kind of classic philosophies for saving power. Cool. Pause for any more questions. Cool. Okay. So yeah, that's maybe any last questions on power or energy. Okay. Well, let's move on then to talk about design space exploration, right? So let's get a little bit of motivation and context for what we're talking about here. So in all quarter, we've been saying, we want to build these parameterized generators because with the parameterization, our generators are much more flexible than a single instance of a design. So that way, hopefully we can get more reuse, right? Where someone maybe has different, needs, and that way, we can set those parameters and match their needs, right? Well, sometimes it's not just a matter of getting those parameters set for functionality. Like, yes, I need something that has this many bits wide. It's actually also a matter of performance, right? Where it's like, how am I going to set various things, right? As you saw, maybe remember in the matrix multiplication homework, where you had that parallelism knob, where you choose how many, multiplications it's doing in parallel. That's a knob, right? And how do you choose where that knob should go, right? And so the way people often refer to this is what's called design space exploration. We're basically kind of, going to say, of all the possible things we could do, which one should we actually do, right? And of course, it's easy to say, oh, I will, make every possible hardware design and evaluate every possible hardware design and pick the best one, but you probably should have some doubts about it because that's clearly not possible, right? Clearly it's going to be intractable to do that, right? So instead we're kind of realize, how do you identify and kind of scope out the extent to design space? What are kind of the possibilities? And then within those possibilities, how do you go about picking the right design? So first off, you might ask yourself, well, what does right even mean? So you got to figure out what are your metrics, what metrics we're considering, what are we worrying about, that kind of stuff. And then you may have plenty of scenarios where you find out, what? I have multiple optimization metrics. How in the heck do you optimize for multiple metrics at the same time? And the answer is you got to kind of carefully navigate some trade-offs and kind of navigate this, or perhaps identify constraints, or etc. It's kind of a broad thing. There was a chat comment that came in. I think I missed the joke, but thank you for sharing. Okay. So for science-based exploration, or DSE for short, let's kind of talk about this, right? So what kind of metrics might you consider? Well, based on today's lecture, you might say, oh, yeah, I can worry about power. Power is a really important metric. And power is a really important metric. It's often like the biggest limiter in designs, right? If we weren't worried about power, we could have chips that run at unbelievably high gigahertz numbers. We could do a lot of things, right? But, perhaps performance, right? If you're building hardware, there's implicitly some sort of performance target here, right? Because if you really care about performance, you should probably buy an off-the-shelf processor and just write software, right? That'd be much easier, right? Much I'd love to make writing hardware easy and chisel and generators. It's much easier to buy a commodity mass market processor, to be an application core or a small embedded microcontroller, and just write code, right? Rust, C, whatever you want to do. So if you're doing specialized hardware of some sort, whether it be a processor or anything, you have some performance desire. And so if you have some performance desire, you're definitely thinking about it as a metric. And the question is, performance, how does it matter for your case, right? Are you worried more about latency or throughput? So the really insightful question from Chao was asking, wait a second, here we are working at the chisel and fertile level, and at that level, how am I supposed to get these metrics about like things like performance or area? Like that's kind of detached. Yes, that's absolutely correct, right? Because At the level of chisel, all you know is how many cycles something will take, right? So when you run in simulation in Treadle or Verilator, you can see for my design on this, test bench stimulus, how many cycles it take to solve this problem, right? So all you know is cycle count, which is one measure of performance, but in terms of turning into an absolute real world time, you need to know the clock frequency, right? In order to know the clock frequency, you need to know what's going on. So the answer, of course, is yes. There's, as we talked before, you have your hardware design tool flow that's going to take your design and map that to a target technology, whether it be an ASIC or an FPGA. And so, yeah, all these things about power, performance, area, these things are all going to kind of come down to how your design is mapped to technology, right? So a better or worse mapping will change those. A different technology choice will change those. And so from our level, the tools we've used so far in this course, we kind of are oblivious to them, right? Unfortunately, that's the case, right? But fortunately, if you want to learn more, you definitely can. So here at Santa Cruz, we have 2 courses that kind of go into this. There's 222A and 222B. So 222A is going to cover more of kind of the circuits and VLSI information, introduce you some of these tools. And 222B, they really kind of run the tools a lot to the point of actually designing small chips, right? And so actually, when I taught that course last spring, my colleague, Professor Matt Goodhouse, was actually really exciting. He had the students not only design their own chips, they actually got fabricated by Google Skywater. So you can totally do that, right? But in order to get a concrete number about area, power, performance, either you get some sort of way to model it, or you need to actually run this through a tool flow and actually get the results. And even the tool flow, they're going to tell you a model probably, right? You don't really know for sure until you actually build it sometimes. For this class in the Chisel Fertile world, usually the kind of standard practice is to turn it to Verilog and to pass off to existing tool flow. One of my pipe dreams as an instructor is for someone to build a lightweight Fertile pass that can take the Fertile for design and make an analytic model. So it wouldn't be perfect, just a model to try and give you an approximate, area and power consumption. And there's reason to believe this is possible. Intel had something like this as a research prototype, 4 years ago, more than that. And it's a little bit too bit rotten with the newest version of Chill, so we can't use it for this course, but something like that would be great. So great question. So to get these metrics, sometimes there's a long loop, whereas, you have your design, you run through a lot of tools, then you get the number out way later on. And so part of that design space exploration kind of question is, well, is there a way you can kind of answer some of these questions perhaps quicker or easier or faster, right? Keep that in mind. Good point. Okay, so of the metrics, right? Power, performance, area, PPA, we've talked about these, right? These matter. What's interesting is when you're designing for the real world, there's actually other things that are important. Sometimes it's not easy to quantify as a metric, right? Things like usability, things like security. Or as we talked a little bit about, what about manufacturability, right? Here's the chip I want to design, but is this actually easy for, TSMC to actually fabricate, right? Or testability, right? Is part of making that manufacturability, how easy is this chip to test? Or maybe you really care about fault tolerance. Maybe this chip's going into a satellite, in which case, when you're in space, you don't have the atmosphere protecting you, so you're really worried about handling all that, solar radiation up there, right? And how can you handle that and other types of radiation from space to make sure your chip doesn't break? And so you have what's called a rad hard or a radiation hardened chip, right? And so there's all sorts of various metrics to kind of be aware of, right? So how could you possibly optimize too many? I said one is hard enough, doing multiple metrics is hard, right? So what else can you do, right? And so what knobs you have to turn to optimize these metrics? And so we're already kind of assuming you have some generators in mind, right? Or either built or already kind of planned out, right? And so when you're kind of figuring out what knobs you turn to kind of explore this design space, right? If you have a single design instance, that's going to have perhaps, have quantified metric values for all these things, right? But if you actually want to talk about design space, you're considering multiple designs, right? And so generators make it easier to consider even more designs because you can easily make other variants by turning these knobs, right? And so in terms of the parameters, right, there's kind of the ones that are external, which are kind of set by the problem, right? You need to, say a chip that decodes video. I want you to do H.265 as the protocol, the codec I want you to do, right? That's an external parameter kind of telling what you need to do, right? And there's the internal parameters, which is kind of things we're controlling, right? How we're going to implement various things. And some of these are maybe simple knobs, like how wide this bit field is or how deep this queue is. Otherwise, it's going to be pretty big architecture choices, right? Okay, I'm going to do a totally different architecture in this case. I'm going to do this kind of, top-down approach. Use a bottom-up approach. Use a middle-out approach, right? Whatever you're doing. And so it ends up being a lot of knobs, right? There's the ones that kind of set from the outside as external parameters, but the internal parameters, there's a lot of them, right? And these are things like what architecture you're using and how you're structuring things. There's a lot of knobs here, right? And so how can you go about this, right? Number one is to kind of have a serious design conversation about, well, what metrics really matter, right? Early stages, it's easy to kind of list a lot of things on your wish list, right? But you can't do them all, right? So how are you going to kind of get through that, right? And so first off, if someone gives you a metric, you should ask yourself, is that really important? Or is that something that's, just being overly cautious? Does it really matter? Many times you can take a metric and say, rather than just being a metric to optimize, you can turn it into a constraint, right? For example, maybe for your application, power doesn't matter as long as you're under a watt, right? So if it takes 0.99 watts or 0.7 watts, actually that doesn't cause any benefit for your system, but it needs to be below 1 watt. That's the important constraint, right? So that's you can turn this metric into a constraint, which makes it kind of much easier for you to optimize, because that way you can have fewer metrics to optimize, right? And then amongst the metrics, you may say, well, originally I had 6 metrics, and then I got that down to, let's say, 3 by turning 3 of them into constraints. So I have 3 remaining metrics. Are all of these metrics equally important? Probably not, right? So maybe you can figure out if there's a kind of a precedence order or kind of a way to weigh these metrics, because, it's going to be hard to improve them all at the same time, right? And so you kind of have a notion of how you want to trade off various metrics, right? I want to improve metric A at the expense of metric B, for example. Okay, and then that's just getting yourself a handle on what the problem is, right? Okay, I know these metrics that really matter. These other metrics that turn into constraints, and the ones that do matter, here's kind of my prioritization of what these metrics are important, right? Then when it comes to the parameters, so you kind of need to do a similar kind of sanity check, kind of shakedown on them, right? And it's easy to say, oh, these are all the parameters, and consider all options, right? But does that make sense? A lot of times, no, right? Many parameters are coupled, right? Where if you change this parameter, you should change another parameter. And it's like usually really clear. For example, this block produces things, this other block consumes directly. There's no, lag or any gap. So there's no point in building higher production that can be consumed or higher consumption that can be produced, right? And so if I change the producer throughput, I need to change the consumer throughput, and I change those in tandem. So you can find a lot of your metrics are coupled, right? And so you can just combine those, right, and tie them together. Additionally, kind of studying your parameters, you may find some are more impactful, right? Maybe there's some queue sizes that really don't matter. It's a small thing. I change it. I don't see any freaking difference. That's less important than a really big thing like, oh my gosh, how many, instances of this giant core block I'm going to put down, right? And so kind of get a sense for your parameters and understanding which of these parameters are ones that are really important, really impactful, and which ones are independent versus which ones are coupled. Some are very coupled, in which case you can reduce design space by changing them together, right? If I had 2 variables, you have the product of possibilities, but if it turns out you should be changed together, then you only need to worry about one of them, right? So it's kind of like you divide it by factor of n, right? Cool. Okay, so we've tried to kind of tame our design space. We said, you know what? Of all these metrics, these are the ones that really matter. Turn some metrics into constraints. For the parameters, we've kind of, identify a couple parameters. We identify which ones are truly independent, which ones we can perhaps ignore. So we have a kind of a more concrete, less absurdly over problem, but at some point, you're still going to kind of need to go in there and explore that design space, right? And so how would you go about doing this? Well, there's you can do an entire course on this, but for today, we're going to get a long 1-slide summary, right? So what can you do? Well, the truth is, the reason why it's such a long topic is it's actually very application dependent, right? And the reason why is that this is, an optimization problem, right? So those of you who have, maybe an ML background or just more formal optimization background, that, if you have a non-convex optimization problem, sometimes that's really hard to solve, or really hard to solve optimally, right? And this is kind of that case. In this case where, someone's problem isn't as simple as just, a mathematical function. You're actually trying to talk about an entire hardware design, right? Which to instantiate an entire hardware design and actually push it through a tool flow can be a very big effort, right? And so to kind of navigate this, any way we can use human intuition to kind of guide us and tailor this to the actual problem we're solving is really, really good, right? And the reason why is because we can't consider all options, right? We can't just brute force this, right? We have to have some sort of intelligent way of navigating the design space and kind of seeding our search and that kind of stuff, right? And so, how do you go about doing that? Well, normally you have a lot of human guidance, right? You can kind of know, like, let's say I'm building a chip and I built the chip last year, and the chip last year had these parameters, and well, this year we're trying to improve performance by a certain factor, but we also have this much better implementation technology, and we also made these algorithmic improvements which we put in the hardware, right? So we know, okay, wait, well, I got this much speed up here, this much speed up there. I might just guess, scaling these things, this might be a reasonable design point. Might be a good way to kind of start your design search, right? But if you're actually talking about trying to explore all these design points, what are the ways people do this historically? Well, all sorts of methods, right? You have things like, branch and bound, where try things out and see if it's doing better or not and kind of keep going. Dynamic programming, randomized search. Those are kind of the classic algorithms from, decades ago. Obviously, you can do much more sophisticated things. You can do genetic evolution, where you kind of have, you have design and you try perturbing it and see if it's an improvement and kind of go from there. Or, of course, things like tons of machine learning algorithms, or, all sorts of gradient descent kind of like things, of course, right? Simulated annealing like things, right? All these kinds of different algorithms, right? But the point is, all these algorithms, what they're doing is they're trying to intelligently explore the design space, because exhaustive search is not possible, right? So somehow you're going to try to go through a subset of the points and kind of learn something about it and pick the right thing. And so the question is, how would you actually go about doing this, right? Historically, people kind of did this in two phases, right? They would kind of do their best to make analytic models, actually, like pen paper models. Okay, well, I think if I design the system this way, it's going to take this much performance, this much power, here's the kind of, hand wavy hand, and they would just use these models to kind of, solve some integrals, or what we're doing to try and get an early kind of starting for design point space, right? And then they only have the resources to kind of, fully implement and evaluate maybe 2 or 3 options and compare those and pick the best one, right? Of course, you have more sophisticated models, right? You get some sort of, statistical-based model, ML-based model, try and more carefully predict how certain options will do, and then you can kind of explore design space using models, and then you still may want to implement multiple instances to try and see which one pans out, right? Again, this modeling and simulation, right, it's really important. So there's a really famous example in the last few years where people are probably very familiar with right now. AMD is doing really, really well selling CPU cores, right? 10 years ago, AMD was not doing so well. And what happened? Well, they made a very ambitious architectural leap. And this is the bulldozer design. And guess what? The simulation and modeling folks blew it. They made certain assumptions in their models that did not pan out. And they really missed on how it's actually panned out when it was actually built. And so as a result, when that chip was actually made, it was not a great chip, right? It didn't sell well because it wasn't good. And there's only situations where in the early design exploration, they used models and they did their best efforts, right? And the models were wrong. And after 3 to 5 years of product development, at large scale CPU chip scale, by the time they figured out that it was wrong, it was too late, right? They were in deep, And so sometimes modeling, can be really helpful, but you gotta be careful with it too, right? And so what's nice is with Chisel, we have some ability to take some of that risk out of it, right? With a generator, rather than saying, I'm going to guess, it's easy, rather than, how to think about performance, change these parameters, let's going to change the parameter, right? And see how it runs, right? How it actually runs through the tools, right? It's like, oh, how might this thing map when it gets to map technology? Well, guess what? If I use the same tools to map my candidate design, then use to map the final design, I have a pretty good idea how it's going to turn out, right? And so this is why I recommend kind of closing the loop early. Use your CAD tools for your specific technology to kind of, start getting numbers early on. And you can kind of start getting a sense for this, right? And kind of honing in, right? When you first start on day one for a brand new design, you may have no idea what is the reasonable amount of resources you can use, right? I can put down, 10 of these blocks, or can I? Can I fit 10 of these blocks? Who knows, right? And push this through a tool flow and you realize, oh my gosh, those blocks are really big or really small, and I can put more or less of them than I actually thought I could, right? So getting that early feedback from the tools by pushing it through the tools really helps you kind of better seed your design process, right? And so the question that came in from chat is, oh, wait a second, these models, that sounds pretty helpful. Isn't it perhaps easier to use these models to explore design space than actually writing Chisel to that? Definitely. If you're doing a model, an analytic model, statistical model, however you're doing it. And it's easier to change a model than it is to change a real design. That's simple, right? However, Chisel is easier to change than changing Verilog, right? And so if I was, in charge of a company, what would I do? I would do all of the above. I have people doing some early analytic models to kind of see what's even worth doing. But as we start getting into it, yeah, I would start building parameterized Chisel generators and start seeing where we're going with that, right? And the reason why is that sometimes it's really hard to get this right in the model space. Where like the models can tell you sometimes like architecturally this approach is, not going to work at all, or this approach is going to work. It can tell you that sometimes early on. But knowing the exact right parameter value, like I need to have a QDEF of this thing, or how this is going to map technology, it's really hard for models to get that right. And so even if you have a good modeling team, they still have to kind of do multiple design instances at the last second to kind of, fine-tune those parameters and actually start manufacturing it. So you already kind of need that flexibility already. And that kind of flexibility is really easy to do with Chisel. And you can be a little bit more aggressive rather than just, changing a buffer size or something like that. You actually change something a little more significantly because it's not hard to do, right? In Verilog, changing buffer size, yeah, you can do that easily. But to change something much more dramatically with architecture or topology, it's going to be a lot of coding, but perhaps not with generators, right? That's kind of the goal. And so using this Agile approach to try to get this feedback early on, you take a lot of stress off the modeling team, right? But yes, that's kind of the point. When you're doing science exploration, in a waterfall approach, you do DSC first with simulation and models, and then you start building your actual chip, or start designing each block, and then each block has to meet some performance criteria. But it's open loop, right? You have no idea if those performance points are achievable or if they're going to fit in the area budgets. And it's all kind of based on how good you can model. If you can model really, really well, both in how well you actually can build things and how well they're going to perform, then yeah, perhaps you could do waterfall with DSC at the beginning, right? But in practice, it's really hard to get some of these things right. A company like AMD, who has billions of dollars at stake, needed to get it right, and they didn't. And so, yeah, it's important to kind of get this sorted out. Cool, great. These are great questions. Please keep them coming. Okay, so, at this point we're kind of saying, yeah, you have a lot of choice in design exploration. You kind of can do various things, but how might you even explore this, right? Well, one concept I want to kind of leave you with is this notion of Pareto optimality, right? And so this occurs when you get to a situation where you've done everything you can to reduce the number of metrics, but at some point you have still greater than one metric left, right? So if you have multiple metrics to optimize, how do you optimize multiple metrics simultaneously? Because usually you can't improve them all at the same time. Well, there's a trade-off, right? You have to have a trade-off. You improve one metric at the expense of another metric. So one way you might do that is you might say, you know what? I'm just going to assign a weight to my metrics, and somehow with those weights, kind of put them into a uniform space, and do some sort of dot product of each metric times each weight, and add them all up, and get my aggregate super metric. That's one way of doing it. That's not a great way of doing it. Another way to do it is kind of really understand this trade-off, understand what's possible, right? So to understand this trade-off, there's this notion of Pareto optimality, right? And that is that, let's say in this case, we have two metrics we care about, metrics X and metrics Y. For both of these metrics, lower is better, right? So let's say maybe notice is time to complete solution and power required, right? Lower is better for both, right? And so, naturally, the really fast designs might take more power, and the really slow designs, might take less power, right? And so it's kind of a trade-off there. You go faster or you use more power, So how do you explore that? Well, of all the possible hardware designs, especially all your various parameters plugged into your generators, there's actually a lot of design points, right? And some of these design points are better than others, right? In particular, let's say we have, these 2 points, right? This point versus this point. They have the same Y value, right? So you're having no change in Y, but from going here to here, you've improved X, right? So you don't want to be this point, right? This point, is not good, right? You can save your metric X for no cost to Y, right? So you'd rather be here. And so what you realize is actually you'd rather be on what they call the Pareto Frontier, right? And what that is these are the set of points such that they were what's called Pareto optimal. And that is that for a given metric, it can't be improved without improving it or decreasing another metric, right? Or worsening another metric, right? So for example, this point, right? Let's say we're trying to minimize y. You can't, right? If you go to the right, you can definitely minimize y. However, in order to minimize y to go down, you need to go right. You need to worsen x, right? Nobody's going to be better at y and better at x, right? That's the point. So these darker points here, like black points, right? If you're one of these points, yeah, you could actually both improve y and improve x even, right? So you can be like down here. This point's way better than that point, right? You'd much rather be here, right? You have way less y and way less x, right? So yeah, you want to be on the frontier. So the point is, once you identify this frontier, now you see this kind of clear trade-off knob where you know, for my given problem, if I want to improve a metric, what it's going to cost me, right? You say, you know what? Well, how much I want to improve this. And sometimes the reason why you want to plot this is you might see this knee in the curve. This is very, very common. It's kind of, inverse function kind of curve, and you have this kind of knee. And so sometimes you're like, if I improve it by a little bit, and if I increase this metric by a little bit, I get huge improvements in y. And then at some point, I get, much less improvement, right? And so, yeah, you kind of want to be here, right? Because, at this point, I've got the maximum gain so far, and if I want to get more gain, I can, but maybe it's not worth it, right? So you want to be in this Pareto frontier. And this is kind of point is you want to kind of identify this. And what happens having chisel and generators is that it's really easy to push through a lot of designs through the tools. So turn this problem into a compute problem, right? Just get a big cluster and fire off a lot of design implementations with a lot of tool flows and run the tools many times and see where you are, right? You can kind of see it if you want to identify this frontier. You want to have a lot of points in this graph, right? You want to be trying a lot of things out, and you want to identify this frontier, right? If you only can do a couple points, you're kind of missing the big picture, and you might be, one of these points. You might never realize these other points exist, right? And so, kind of with this, chisel agile approach, we actually do want to try a lot of designs, and set a map into tools and see how you kind of do various things. And these generators makes it easy to kind of do that. Cool. Any questions on Pareto? So, as I said, this shape is very common. In fact, I'm going to show you on the next few slides some pictures taken from research papers that kind of show this occurring in experiments, right? So, for example, there's this wonderful paper by Sophia Xiao for the Aladdin. So, what did she do in her paper? Aladdin's a wonderful tool to do some of this kind of early modeling and simulation. So she had a way to take in parameters about your hardware design, and actually in this case, she's working at a higher level. She's taking more of the application kernel you're trying to solve, and then she was considering many possible hardware architectures, many possible things, and then there was a way for given architecture to kind of quickly model its power and energy, and kind of map things out. And what you see here is that in this case, looking at execution time and power. So lower both of these is better, and you can see there's these Pareto frontier, right? Many design points, like over here, for example, it's not the point you want to pick, right? You'd rather, for a given, performance, with no loss in performance, you can just use less power going down here, right? It's almost like a factor of 3 power could be saved by 0 loss in performance, right? You should do that, right? Or if you're here and you want to save, go faster, but at the same power level, you can be going way faster, right? And so you want to be on this frontier. Now, this particular paper, right, she's considering a lot of different knobs, and so all these points, it's very hard to kind of categorize them all. In this case, she's looking at various features. So this paper is actually designing, like she did earlier, a matrix multiplication circuit in a very classic problem, right? And looking at, okay, well, how many bytes per cycle am I taking up for the bandwidth? And you see, of course, if I have, low bandwidth, then yes, I'm going to have kind of shoehorn into a high, low performance regime, but guess what? Also going to be very low power, right? As you crank the bandwidth, yeah, you can go faster, right? But you can kind of see these various things. And she did her best with these arrows to kind of annotate some of the design trends. Sometimes when you get these kind of scatter plots looking at DSC, it's kind of hard to differentiate. You have, a zillion metrics you're changing. Zillion parameters you're changing. How do you kind of choose to plot it? And you kind of are forced to only plot like 1 or 2 dimensions at a time. You can kind of change your point shape and your color, but then you're kind of, doing multiple plots, seeing any kind of trends, right? But you still get the point across, right? That, you can see depending what your goal is, if you really want to minimize power, you better have kind of this design. It's going to take longer, right? So you're using less power, it's going to take longer, but you're going to be happier with a lower L1 bandwidth. If you really want to go fast, it's going to cost you some power. And you're going to need, you see these darker colors, you're going to need to use, orange or yellow, 120, 26 bits per cycle. You need to have a higher bandwidth L1, right? So you can kind of see this trade-off kind of played off here, right? So here's an example of a DSC in practice. This is one of these really pretty Pareto Frontier kind of plots. Another one of these is from a paper, and this one's also generating this from a model rather than from Chisel. And what they do in this case, actually, so the prior one, she actually, synthesized, or, within her model, these architectures and push them through her model. This one's like a model from the beginning. It's like model on model on model. But some really interesting trade-offs, right? This one's a paper from now 12 years ago, but they're just saying, you know what? Of all possible process architectures, we just consider, some trade-offs, right? So there's some interesting insights in this paper to kind of figure out how to make these models. And they're kind of considering, okay, well, for a given process architecture, for now, they're going to think about maybe just two metrics, right? Or sorry, two parameters, right? Is it in order or out of order? And amongst, in order, out order, how wide is it? Is it 1 wide? Is it 2 wide? Is it 4 wide? So those are some knobs. Another knob you can turn on a processor is what frequency you're operating it at, right? And so, for a given frequency, you're going to need to set your voltage appropriately. That's DVFS. But also realize for a given processor, as you change the frequency, that's not going to have a perfectly linear impact on performance, right? You realize, of course, that for things like, talking to memory, at different frequencies, the apparent, cache bit space needs going to be different, right? Because, if you're running at one frequency and then you're running at a different frequency, it's the same amount of real-world time to get the data from memory, but it's going to appear to be a different number of cycles. So there's going to be some kind of changing there. And so you can see that in this paper, what they're doing is they're saying, we're going to try these various architectures out. Say we'll try a really simple in-order 1 wide core, down here. And then we'll see what happens, right? And depending on what performance you want, so in this case, higher is better. So that's why the curve's going a different way in the prior gap. So rather than being lower is better, this is instructions per second, million instructions per second, MIPS. So higher is better. This is energy. So lower is better for energy. So that's why the curve's kind of, mirror image we saw a second ago. You can see this kind of trade-off emerges, right? Where, okay, well, the 1 wide in order, actually is the most efficient for really low performance, right? Because guess what? It's a simple design. It's a lot less hardware to toggle, and it can do that well, right? And guess what? If you want to go a little faster, what should you do? Well, it turns out the in order 2 wide is going to be the next best one, right? And this kind of guide at the bottom is kind of telling you, they care about the underside of this curve. That's the Pareto Frontier. And what's kind of interesting is you see, for example, that, from this exploration, we're kind of going through these architectures, which one's the most efficient for a given size. You see, okay, in order 1 wide, in order 2 wide, in order 4 wide. It's actually a pretty narrow window. Out of order 2 wide. Wait, what happened to out of order 1 wide? That's this one, right? And as you can see, that design point or set of design points doesn't make sense, right? That, for any point of performance regime you could care about, it's burning more power, right? Compared to, the in-order cores, for when you set the frequencies appropriately, for comparable performance, it takes more power, right? And then, compared to bigger cores, it's just not as high performance, right? And so that thing is, Pareto inferior, right? It's just never going to win out. But you see, you really want to go fast, you're going to need to go big, right? You need to go out of order 2 wide or an out of order 4 wide. And you see, if you scale down the out of order 2 wide to a lower performance point, turn down the frequency down, it does save power, right? That's the DVFS at work. However, at those other points, these other simple architectures are going to be more efficient. So you can kind of see this trade-off playing out here. So here's another example of this kind of thing winning out. And it's kind of interesting trade-off. And so once again, what matters is this Pareto Frontier. Just, if I care about trading off performance versus energy, I really want to be on this outside Pareto Frontier. I don't want to be back here kind of making arbitrary choices. I really want to be out here. And so that's what I want to kind of leave you with, this kind of appreciation for, having to make a trade-off between multiple metrics is a very common real-world design problem. And you want to make sure you're making that trade-off, fully informed on that Pareto Frontier. You don't want to be, somewhere in here or, somewhere in here where you're kind of just wandering about. And yeah, some points look better, some points look worse, but you aren't at the frontier. You want to be at that Pareto Frontier. Cool. Any closing questions? Okay, well, with that, I'll thank you folks for another lecture. And remember, on Monday, please be sure to send us that link to your repo of initial proof of concept working. It doesn't be fully done, just something working. I'll open up the assignment in Canvas. Yeah, there'll be a Canvas assignment. You can post a GitHub repo link. And really, I just want a GitHub repo link. It's okay if it's private for now. You just need to add myself and the TA mode to it. And we just want to see a README in there so we can clone it and run something to see something working. Cool. Have a good one, folks.